All right, electrolytic cells. Now this is a lesson right after electrochemical cells, the voltaic, galvanic cells. Electrolytic cells are just slightly different. There's a lot of similarities here, but there are some differences as well. So let's talk about this. The general form of a reaction can be written as, okay, when we're talking about electric potential and stuff like that, reactants are reversible reaction here with products and electrical energy. Okay, now it's very important to note that what we've studied so far here is the spontaneous electrochemical cells, right? That move forward on their own. So if you're giving off energy, right, if the voltage is, positive, what we learned in last lesson, then that would be spontaneous because we're giving off energy. And that is the galvanic / voltaic type cell. What we're focusing on today is the reverse direction. Okay, so if you have now reactants and products are relative, right? So if we start with reactants over here, these are reactants now, and we have to input electrical energy, we can go the opposite direction to get products. Okay, so this can be reversed. It's a reversible reaction. So when we go in the reverse direction where electrical energy is required to let this to have this reaction happen, that's the electrolytic type cell, okay, the electrolytic. So it is possible to construct a cell that does work on a chemical system by driving an electrical current through the system. These cells are called electrolytic cells. Okay. Blanks here to drive, where would be by driving, by driving an electric current through the system. These are called electrolytic cells. Electrolytic, you want to write in there. Electrolytic cells, like galvanic cells, are composed of two half cells. One is a reduction half, the other is oxidation. The direction of electron flow in electrolytic cells, however, is reversed from the direction of spontaneous electron flow in galvanic cells. So we have to get our head wrapped around, and this is tougher than a brand new concept, I would say, to remember, because you've just learned, right, where the electrons go in a voltaic galvanic cell, and now you have to think about applying energy to go backwards. So if you think about everything the same, except the electron flow is reversed, and there's an electrical energy that's input into that wire, that's kind of close to what we're dealing with today. So when the electron flow is reversed from what we just learned, that's an electrolytic cell. Okay, so the definition of a cathode and anode still remain the same, where reduction takes place at the cathode. So this is not a blank, but still important. Okay, reduction does take place at the cathode, and oxidation occurs at the anode. But because the directions of both half reactions have been reversed, the sign, but not the magnitude, of the cell potential has been reversed. Okay, the sign of the cell potential has been reversed now. Yeah, so before, when we had lots of positive voltage, right, in those examples that we did, now if we're applying electrical energy to reverse the process, we're going to get a negative. Well, not everything. The cathode anode's sort of still the same, but you reverse some things. Yes, that's right. Okay, electrolytic cells have a very similar to galvanic or voltaic, in the sense that both require a salt bridge, both have a cathode and anode side, both have a consistent flow of electrons from anode to cathode. It's not a blank, but it's important. Flow of electrons from anode to cathode. However, there are also striking differences between the two cells. The main differences are outlined below. All right, so here's a diagram to help all you visual people out there, like myself, kind of see what's happening. So in a galvanic cell, again, this is what we just learned here, galvanic cell. Here's the anode, so electrons are flowing away from the anode. They have the ability to do work, like on a light bulb. They could light up a light bulb or something, and they're heading down here to the cathode, okay? That's the galvanic cell. In the electrolytic cell, all right, now this diagram is drawn with the electrons flow in the same direction, but with the anode and cathode, the signs here reversed, okay? So it's a little bit different. We have electrical energy plugged in from the wall or whatever, and it's actually driving the electrons in the opposite direction. Okay, so they're going from the the cathode, or they're going from positive to negative. I guess that's the difference. Okay, positive to negative. So here is negative. I don't know what you want to put. Negative cell to positive. Okay, and this is from positive cell to negative. That's the one big difference. Okay, so it's driving it in the reverse direction. So I'll just read this along. You have this in your note. I guess there's some blanks for you too. Electrochemical cells. Okay, so the first one, just review electrochemical. A galvanic cell left transforms energy released by a spontaneous redox reaction into electrical energy. So I'm going to highlight spontaneous there for you as a blank. That can be used to perform work. The oxidative and reductive half reactions usually occur in separate compartments that are connected by an external electrical circuit. Okay. In addition, a second connection allows ions to flow between the compartments, shown here as the vertical dashed line. So here's kind of the salt bridge or whatever. Okay. And it's necessary to maintain electrical neutrality. The potential difference between the electrodes, the voltage, causes electrons to flow, causes electrons, where are we? Oh, here we go. Causes electrons to flow between. Yeah, I highlighted the wrong electrons. Sorry. Or ions. Sorry, allows ions. My bad. Ions allows ions to flow between the compartments. Shown here as the dashed lines. So that's your blank. Sorry. And this is necessary to maintain electrical neutrality. Okay. The potential difference between the electrodes causes electrons to flow from reductant to oxidant through the external circuit. Now. Okay, conversely, now the electrolytic cell, let's read about that. In an electrolytic cell, an external source of electrical energy is used to generate a potential difference between the electrodes that force the electrons to flow, driving a non-spontaneous redox reaction. So the electricity is pushing the electrons sort of the opposite way from what it would naturally want to do. Only a single compartment is employed. So back up to the, if you look at your diagram there, notice that there's no, technically there's a salt bridge, but there's no separate compartment. Okay, this is all in one. Okay, so this is all one solution. All right, where here there's separate with that kind of separate salt bridge usually, right? So this, there's no, it's all one solution. So it's going to be all in one big beaker, let's say. For the electrolytic, yeah, for the new one. So only a single compartment is employed in most applications. In both kinds of electrochemical cells, the anode is the electrode at which the oxidation half reaction occurs. Okay, the anode is the oxidation half, and the cathode is the reduction. So anode and cathode. But the electricity that's forced through it all switches those, which is the anode and which is the electrode. Or sorry, the anode and cathode. Okay. Okay, so here's another chart to outline some differences, another way to look at it. So let's fill in these blanks. Electrochemical cell on the left, a galvanic or voltaic cell converts chemical energy into electrical energy. An electrolytic cell converts electrical to chemical, so it's reversed. So chemical energy to electrical in the first type, and then electrical into chemical energy in the second type. Galvanic cell, here the redox reaction is spontaneous and is responsible for the production of electrical energy. In the electrolytic cell, the redox reaction is not spontaneous and electrical energy has to be supplied to initiate the reaction. Okay? Oh, I guess in keeping with my consistency here, I'll do blue for your blanks. Blue for your blanks. Okay, third one, the two half cells are set up in different containers being connected through the salt bridge or porous partition. And on our new electrolytic cell, both the electrodes are placed in a same container, or in this same container, in the solution of molten electrolyte. So there's no separate salt bridge. When you hook it up to electricity, you have this constant external source, so you don't need the salt bridge to kind of keep it perpetuating. And we'll talk about applications of this obviously here soon too. Okay, down here the anode is negative and cathode is positive. The reaction at the anode is oxidation and at the cathode is reduction. In this new cell, the anode is positive, okay? So again, this is part of the reversal. The anode is positive and the cathode is negative electrode. So as part of the reversal, there's still the same oxidation reduction is happening at the same electrode, but the anode is now positive and the cathode is now negative. Okay, so that's part of the reversal. Okay, if this is reversed, it's reversed. Okay, another reversal right there. And finally, another important point, the electrons are supplied by the species getting oxidized. They move from anode to cathode in an external circuit. And here in the electrolytic, the external battery or electronic supply from the wall or whatever supplies the electrons. They enter through the cathode and come out through the anode. Yeah, question. I'm sorry?
What would they use in electrolytic cells?
Yeah, that's I mentioned we're going to talk about applications here towards the end of the lesson. Yeah, we're getting there. One obvious one for me is electroplating. So you hook up an electrical source and you can plate, let's say, gold onto a ring, or you can plate silver onto a coin, or something like that, or you know what I mean. So that is a non-spontaneous reaction. They can force that, and that's one kind of the one that pops to my mind. But there are others. Electrolysis of brine, aluminum recycling, purification of ores, things like that. So we'll talk about those shortly. All right, electrolytic cells. To explain what happens in an electrolytic cell, let us examine the decomposition of liquid or molten sodium chloride. Important to note, this is not aqueous. This is liquid sodium chloride, okay? So don't get confused. This is liquid sodium chloride. We don't have any water molecules in here. It's not aqueous anything, okay? But if we look at this, okay, the reaction is written below here. So it's a reversible reaction, and of course, if you had sodium placed in chlorine gas, they would react, and naturally, spontaneously, they would create sodium chloride liquid, okay? You've got a chunk of sodium, place it in chloride gas, it would react pretty violently, and it would form sodium chloride liquid. The disassociating the liquid into solid and gas takes energy. We have to zap it with electricity. Okay, that's non-spontaneous. So if liquid NaCl is placed in a container and inert electrodes of carbon are inserted, okay, so how would we actually do this? Well, we'd need some electrodes, and those electrodes wouldn't be able to be sodium or chlorine or like that, anything that's involved there. They would have to be just inert electrodes that we can actually pump some electricity through, because we're interested in what's happening in the solution. We're not interested in changing this into metal or this into ions or whatever. So these electrodes are neutral, they're separate. This is how this works. So separate inert electrodes of carbon are inserted, and they're attached to the positive and negative terminals of a battery. An electrolytic reaction will occur. Okay, so I'm going to zoom in on this diagram, give you a minute to copy this down. So this is how this reaction above would sort of happen here. Okay, so again, these are carbon electrodes. We have a battery hooked up, and this battery or external power source would drive the electrons here to the right. Okay. Yeah, that's right. It's a solid carbon electrode. Yeah. So it would be kind of like dark, I guess, probably. Like a dark graphite kind of thing. All right, so what's happening here in this diagram? Electrons from the negative terminal of the battery, okay, travel to the cathode. So here's the cathode. So electrons are going this way, Here's the negative side, here's the positive side of the battery. And they're used to reduce the sodium ions in the solution, here are the sodium ions, to sodium metal. Where are we? To sodium atoms. Okay, so again, we have liquids NaCl in here, and we're trying to create sodium solid and chlorine gas. Okay, so with this liquid NaCl, we are the sodium is picking up electrons to become sodium solid here. The sodium will plate onto the cathode as it forms. The sodium ions are migrating toward the cathode. So here's the ions are migrating toward the cathode, and we have sodium solid forming on this cathode. Okay. 2, the negative chloride or chlorine ions migrate towards the anode over here and release their electrons. So remember, electrons are being pulled now from this external source. They're being pulled from this electrode, so from the solution. So the chloride ions have extra electrons here, negative, and so they're donating their electrons, and they are oxidized to form chlorine atoms. So these little dots that you asked about there, that would be the chlorine atoms, the chlorine gas, I guess, that's bubbling inside here. Okay, so chloride ions giving up their electrons to become chlorine, like sort of gas bubbles here. Okay. Now, if you want to collect those, I guess you'd have to have some kind of beaker or something, trapping this, right? I guess, and they would collect up here because they're gas. And so, the chlorine atoms will combine together to form chlorine gas and bubble away. That's point number 2. Point number 3, as you continue to look at your diagram, if you want there, I'll pop back up to it. But note that the site of oxidation is still the anode and the site of reduction is still the cathode, but the charge on these two electrodes have reversed. Anode is now positive and cathode is now negative. Those are very important points for you to remember. Anode is now positive in this case. Cathode is negative. The conditions under which the electrolyte cell operates are very important. The substance that is the strongest reducing agent. Now this is important because you might not know exactly what's being oxidized and reduced, so how do we figure that out? The substance that's the strongest reducing agent, that's the substance with the highest standard cell potential in the table, will undergo oxidation. Okay? So the strongest reducing agent will undergo oxidation. The substance that is the strongest oxidation agent will be reduced. If an aqueous solution of sodium chloride were used in the above system, okay, this is a bit of an aside before we get into that. Before we get into this, let's just talk a little about this, okay? So the strongest reducing agent, that is the highest value in the table. Where would that table be again? Is it down here? Yeah. So the highest number in this table, okay, so the ones down here, if you have any, okay, are going to be this. They're the substance, the strongest reducing agent will undergo oxidation. Okay. So that's going to actually lose electrons. All right. So if we go back to the table, I guess, which is here. Okay, so these really want to gain electrons, but when we apply electricity in an electrolytic cell, they really want to lose electrons. Okay, they really want to undergo oxidation. So that's part of the opposite, right? In opposite world here. Okay, so just to clarify that again, I'll just say that one more time. If you look back in your notes, in the galvanic cell, the table, whatever is lowest here, okay, in the galvanic cell is being reduced. Okay, high reduction potential, it's going to be reduced. In the electrolytic cell, whatever is lowest on the table has this highest number is now being oxidized. Okay, so again, it's reverse operation, reverse. All right, let's talk about applications. You might have some further questions that can help you out with it as the questions come up. But let's just finish up here. Applications. So we're talking about applications before. What are the applications? I mentioned the one application that comes to my mind is the electroplating. I want to talk about one of these applications, and then I'm going to get you to research the rest in your own notes. Make notes on the rest, okay, from your textbook. So let's talk about one today. Page 729, Glencoe is where these are talked about. Molten sodium chloride can be decomposed. So molten, that's like liquid. We just talked about that, I guess. Can be decomposed into sodium and chlorine gas, the example we just talked about. The process is carried out in a chamber called a down cell. Okay, so molten sodium and chlorine gas are your two blanks. In a process in a chamber called a Downs cell. At the anode, chloride ions are oxidized to chlorine gas. At the cathode, sodium ions are reduced to sodium metal. At the anode, chloride ions are oxidized, and at the cathode, sodium ions are reduced. So the net cell reaction is this. You have to write this down in your notes here. So 2 sodium atoms plus 2 chloride atoms produces 2 Na liquid and then chlorine gas. So the idea is, I guess, to get solid, but the liquid is what is produced initially. The importance of chlorine gas is paramount in cleaners, water purification, and the production of plastics, paints, and insecticides. So chlorine is pretty important in our everyday lives. And also sodium, maybe not as common, in our everyday lives, but sodium is pure sodium is a coolant for nuclear reactors, and it's used in sodium vapor lamps, among other things, but those are the initial things. Okay, so that's one application of electrolysis to produce these important chemicals for industry and that sort of thing. Okay, again, just due to time here, partly, and also I just want you to do your own reading and research on this. These are a few things that you'll find in your textbook. Feel free to research online as well. Electrolysis of brine, aluminum recycling, purification of ores, and electroplating. So make your own notes on this. You don't really have lots of room in the handout that I gave you, but just take a separate piece of paper and add to your notes, I guess, some of these applications, or at least read and understand them, applications of electroplating. I'm sorry, applications of electrolysis. So I did give you some problems here in your notes, as well as some questions from the textbook that I'll get you to work on to solidify this lesson. We don't have a whole lot of time in class here left, but I'm going to get you to fill in this chart with the appropriate ions. See if you can work this out. I'll give you the answers to that tomorrow. And also there's question number 2 here, so a bit of a multiple choice question, and also asking you to find the standard cell potential for an electrochemical cell with the following reaction. Okay, standard cell potential, the following reaction. All right. So work on those 3, and also your textbook questions, Glencoe text 55 through 59, and actually 57, 58, 59. Those are questions about right here about the applications. So when you do your notes, you're actually doing some of those textbook questions there already. So the textbook questions are referring to explanation of these. So okay, and I'll give you the answers to that in tomorrow's class.